Hello everyone. Thanks for the introduction, Mega. I hope you all had a great day one, and it's great to be starting day two of this exciting conference. So I'm Kamal. I am a front-end developer. I like building web applications. I like building web applications using React, and I also have been working with Postman on their web and Electron applications. And I also lead a team at Postman focusing specifically on improving the performance of the desktop app. So I thought, why not do the best of all three worlds and talk about improving performance of an Electron and a React application in this talk itself. So Electron is basically a cross-platform application that let you build desktop apps by using your knowledge with JavaScript, HTML, and CSS. So Electron claims that if you can build a website, you can build a desktop app. So it got me thinking. So if you can take the learnings of building a web application and build a great desktop application with it, can you also take the learnings of improving the performance of web application and improve the performance of desktop apps using the same concepts and principles? And can you also learn new stuff by looking at Electron application specific constraints and extend them into the web app and improve your React app as a side effect as well? So in this talk, I'm going to be covering a few details about what are the tips and tricks that you can use to extend and improve the performance of your Electron and React applications. And even if you're not building an Electron app, some of these concepts might also extend into your normal React web app as well. So just to get started with Electron, it is really easy to get started with a very basic Electron. So on the Electron app, on this screenshot, you see Electron Fiddle, which is a tool equivalent to Code Sandbox. It helps you put together quick demos with Electrons across with Electron app across multiple versions. So just to kind of show an idea of what this looks like, you just have an entry point file that you can call main.js, and then you can point Electron to that entry, which basically spins up a new app like this, which gives you the user interface for the Electron application. So all you need to do to get started with an Electron application is a very simple Node JavaScript file called main.js. And in this file is where you're going to be starting to open a new UI window. And in the UI window, you can point it to an index.html, which is going to be your React or web application using HTML, CSS, and JavaScript. So now let's talk about how you would normally approach performance on a web app. So you're probably thinking at this point, can I use the same core web vitals metrics? Can I use the same dev tools like performance dev tools, memory dev tools, or Lighthouse dev tools on Chrome that you're usually used to and have a lot of advantages with? Can you use all of these into Electron apps as well? So the answer to that is yes, you can. Core Web Vitals also work within Electron apps, and all the Chrome dev tools by default are also available within Electron apps as well. So which you can use them to profile and improve the performance. But there's a slight difference in some of the areas on how Electron apps work and how web apps work. And that might be a surprise to you if you're not paying close attention to it. So let's start with some of these areas as well. So the first thing that the user is exposed to over your Electron app is how quickly can it start up, right? This is equivalent to how soon can your web page load inside a browser tab. So let's talk about what impacts the startup performance of an Electron app. The first thing to keep in mind is launch performance on Electron is slightly different from load performance of a normal website. And the reason for that is your application lifecycle actually starts much earlier than the user interface or the UI window. So you're responsible for starting your application right from the user clicks on the icon inside your shortcut of Windows or inside the launcher of your Mac or Linux operating system. So let's look into what happens actually before you even start opening the first UI window inside an Electron app. So on the right-hand side, you have a snippet of a very small Electron app, which basically has the code to spin up an empty UI window. But you also have this function that's pretty much just downloading catfix. And you have all the node modules that you need to power that function. This unsuspecting require statement to the request node module might actually have subtle impact on how fast can you open the UI window in an Electron app itself. So let's take a deeper look into what does this require statement actually mean in terms of the loading performance. So if we do a deeper performance profile on this particular statement, what we can see is that just importing that node module can block the main thread for about 300 milliseconds, which is essentially delaying the time it takes to open the first UI window by 300 milliseconds and subsequently delaying every other step in the startup performance, which actually means that you're going to be pushing the launch time about half a second or even more. Not to dunk on any particular module, but each module is written with a specific set of use cases and specific set of audience in mind. In this case, the request module is actually extremely powerful and capable with a lot of capabilities, even coming with its own entire database of all the possible MIME types of every single request type itself. But in this case, just to make a request to a URL, you might not need all of these capabilities. So a solution to this problem might be very careful in importing what modules you actually need and inspecting into the cost that they bring into your application lifecycle itself. So the solution is a slightly refactored version of this code, where we are just using an alternate library. So you can use a lightweight library for Node like Axios to make requests instead of the request library, or you can also use the Node.js standard library, which I've kind of demonstrated here with HTTPS. I've also indicated another slight change. So instead of having all your required statements in the file at the top, which is essentially blocking every step of the app launch until all the modules are compiled and executed, this essentially defers all of these modules right until when you actually need them. So the user only pays the cost for these modules only when they enter the flow, making the critical launch path completely open to the important aspects at that time. So now we have talked about what happens before you open the first UI window, right? So let's talk about how do we get UI into the UI window. For an Electron app, there are two ways that you can do this. The first way is to point your Electron application into the URL of your web application, which is very, very close to how you would normally build a React or a web application itself. Just point a URL to your app and then load that into the UI window, and then you have an Electron app with your user interface. The alternate approach that you can do is also package all of your content, the index.html, the JavaScript, the CSS, and the font files together with your Electron app and just point them directly into the UI window as a local reference. Now, there are subtle differences in how these choices impact the launch performance, and that's what we'll go into in depth right now. So let's talk about what happens when you point a URL into the UI window of an Electron app itself. So it's very easy to kind of reuse some of the tech stack and the tooling and everything available to spin up and maintain a web app and extend the benefits of all of that into your Electron app as well. So immediately the advantage of that is going to be to improve and extend all the advantages of techniques like static site rendering, static generation, server-side rendering, or other techniques. But you also have to keep in mind that you're dictated by how soon can you deliver content over a network that is dependent on the user's current conditions. That is going to impact how fast can you launch your application. But this is also very similar to how your normal web app opens in a browser itself. So you can extend the same performance optimization techniques like code splitting, lazy loading, and all of those tips and tricks. Those will also work inside Electron app and giving you a good enough boost itself. You can also prioritize the content closer to the location of the users by opting into CDN and caching the content on CDN. If you're using a framework like Remix or Next.js or any other typical React or web framework, you might actually be getting all of these advantages enabled by default. If you're not, then definitely look into turning them on in your current tech stack. The last point that I want to go a little deeper into is talk a little bit more about extending lifetimes of JavaScript assets in your Electron application. This will come in very handy when you are powering an Electron application that is frequently used. So one of the advantages of having an Electron app is you know exactly that your users are using Chromium technology, because that's what powers an Electron app. And you also know that it is going to be dictated by the unique behaviors of how V8 and Chrome work. you can use this to your advantage by tweaking your application to work really well and taking advantages of the V8 and Chrome optimization techniques. So the one thing that I want to go a little deeper into is how Chrome and V8 cache JavaScript assets. So let's look into what happens if we just provide a JavaScript URL into an application. The first time Chrome is trying to execute this JavaScript, it is going to download the file from network, and then it is going to cache the content of the file on disk and then pass it on to V8. So at this point, V8 tries to compile the JavaScript file and then execute the JavaScript file. The second run of this execution, Chrome does it slightly differently. Instead of downloading the content from network, it is actually going to reuse the cached version of the JavaScript on disk and pass that on to V8. And there's also another difference in the second step, which is V8 also now instructs Chrome to cache the compiled version of the JavaScript as well. This is a heuristic that Chrome and V8 use internally to specifically optimize repeated visits to web pages. And it comes in really handy when you're working with an Electron app, especially if the user has shown an intent to download their app on their machine, which means they're signaling to you that they are coming back to it again and again. This improvement comes in really handy when the user launches their app the third time or beyond, where Chrome can now take both the contents of the file from disk and the compiled output of that and pass it down to V8. This makes V8 very easy to completely skip the compilation altogether and directly go into execution. This can really improve the performance of JavaScript in the blocking steps of the app load lifecycle itself. Now, these techniques come in very handy for an Electron app that might be used multiple times, but it is also something that will work definitely on any web application as well. There are a few ways where you can increase the lifetime of your JavaScript to specifically take advantage of this particular optimization in V8. One of the things is to make sure you are splitting your code chunks between the parts of the app that change frequently and the parts of the app that change less frequently. You can do that with libraries like React or React DOM or your design system or any other node module that you rarely update within your app and extract them into separate chunks. You can also fingerprint those assets so your URL to that asset does not change unless the actual content of that asset changes. You can also cache these on CDN and set a really long lifetime for that on the cache control header over the CDN, which makes it a signal to the browser to use the local version and not go to the network every single time it tries to encounter that file. So now let's talk about the alternate approach of packaging all your content together with your Electron application. What might be the subtle impact of loading content from your users' local operating system and local disk as compared to downloading them over network? So the first factor that it differentiates is you're now restricted to fully doing compute on your user's device, which prevents you to do any other optimization, and you're completely restricted to doing client-side rendering inside an Electron app. However, loading files from the disk can actually be faster than downloading the assets over a network, which is very much dependent on the user's condition at that point in time. However, reading files still come with an I/O and a compute cost. So you have to keep in mind that you don't include really large files because passing compilation and execution of these large scripts can still block the main thread and impact the launch performance of your app itself. So use the techniques like code splitting and lazy loading, even if you're packaging your content locally. The last caveat here is code compilation optimization of V8 does not really extend to files that you're packaging locally. So if this is really important to you, then you can explore an alternate technique like V8 snapshot, which helps you manually generate the cached output and then package them along with your app to get that advantage as well. So we've talked about how the app launches before the UI window and how you can render content into the UI window. So now this is where you are talking about the application's implementation. Since an Electron app does not really have a URL, by default, most of the Electron apps stick to restoring the session that the user had before they quit the app last time. This actually means that you're going to put the user back into some of the state that was in the user's session in the previous session of their app itself. for apps like VS Code or Chrome or like Postman, this might actually have a lot of multitasking capabilities. Like you might have a lot of files open in your VS Code, you might have a lot of requests open in your Postman, which means when restarting your app, you're also simultaneously restoring all of these content at once. So one of the techniques that you can do is to prioritize rendering the hot path or what is really important to the user in this flow, and defer the rendering of any UI element that are in the periphery or in the background. This technique will help you get the user unblocked with their critical workflow first, and then do a lot of the stuff in a deferred fashion until the user actually requests for them. So this pretty much covers what you would have to keep in mind to start the Electron app and what the startup performance of the Electron app actually entails. Now let's go into like what happens after you've launched the app, right? Because if you want a really good experience, it is not just about startup, but also about every single interaction needs to be buttery smooth throughout the entire session of your application itself. So we've all kind of like explored the impact of what happens on a browser if we really block the main thread. Let's just kind of look at that a little bit like once again here, right? So I have a very small code sandbox that is a small React application. So in this app, I just have a counter that is updating every 200 milliseconds. And I have a button that is basically going to simulate a long task on the main thread by just blocking the main thread for 3 seconds. I also have a GIF that to highlight like painting aspects of the web page itself. So now let's see what happens if I just start a long task on the main thread. So you can see the Chrome still continues to paint and composite the GIF, which makes the GIF responsive, but the counter just completely stops, right? This is because the main thread is completely blocking all the intervals, any JavaScript execution, or any layouting that might be happening at that point in time. So now this problem also applies to any Electron apps as well. So let's look into what can we do about that, right? So some of the times this actually might be a side effect of re-rendering large React components. So apply the techniques that you would normally use to split them up into smaller re-renders or even defer unneeded re-renders in some React components. If you also have background tasks on your UI window that are running long tasks on the main thread, split them up into smaller chunks or defer them into web workers that keeps the main thread idle. Let's look into what is different with an Electron app. So an Electron app has this new concept called a main process or a browser process, which acts as an entry point and an orchestrator for everything else that is happening inside your app. So it orchestrates opening a new window and coordinating between windows, and also like interfacing with operating systems and getting all of these workflows together. Now, what happens if we run a really long and blocking task on the main process of Electron? So let's look at a small demo of what this would look like on an Electron app. So I have a small Electron app, which is very much similar. There's a set timeout, set interval updating a counter every 200 milliseconds. I have an input box to indicate like what happens for the user interface. And I also have a button simulating a long task, except this time it is running on the main process of Electron. So let's look at what happens if we run a long task on the main process of Electron. So you can see that the counter continues to run, the GIF continues to render, but the important aspect is that you saw the cursor completely get stuck. And let's look at what happens if we are typing into the input box. So you can see none of my characters appearing into the input box, and they appear only after I have finished my task. This is because the input is actually a native element, and the Electron app requires on the main process to communicate between the UI window and the operating system to get this workflow working. So running any long task on the main process is going to make the app sluggish and prevent these type of interactions to be buttery smooth in your app. So what can you do about them? You can also split up your tasks on the main process into smaller chunks. But most importantly, do not run complex or long tasks on the main process. You can fall back into web workers to run these long or complex tasks, or you can even spin up new node process or a completely hidden background window where you can defer some of these background activity into and keep both the main thread inside the UI window and the main process of Electron idle to have a really buttery smooth responsiveness inside your app. So far, we have covered like techniques for all the cases where you are in full control of your application, but there are some conditions that are beyond the control of the developer. Let's say the speed of the internet in which the user is accessing your systems, or the hardware devices through which they are downloading your app and using them, right? So you might also want to make sure that you have a slightly progressively degraded version or an equivalent of that working even if the user is completely offline or working from a slow network. If you are using a remote origin to render the content into your Electron app, you might be completely dead if the user opens the app when they are offline. To work around this problem, you can install a service worker, which will help you intercept the request even if the user is completely offline with no internet connection. And you can use that to either provide a partially degraded or a fully functional experience on the user's machine without any internet by taking advantage of persistent storage like IndexedDB or even like SQLite file system inside your Electron app itself. So we've covered in depth into a lot of topics into how we can improve the performance of the app, but this is not a one-time step, right? So if you've been looking at improving performance on your hobby project or the place where you work, you always know that performance work is not a one-time task, and it's a continuous, rigorous cycle of dedicated efforts going into it. So I wanted to close this talk by covering a little bit more into how you can have a really effective and a functional loop to repeat this process over and over again to have a really great experience over a longer periods of time. So in my opinion, this process kind of starts with making sure you have a very clear idea of what performance means in your use case. Understand what your product does and measure exactly what flows you want to focus into. Investigate those workflows using the tools that are available to you and find out what the biggest bottlenecks are. Apply some of these techniques that we have covered today to improve the performance of those bottlenecks, and add regression proofing systems to make sure you never encounter the same problem again in the future. And now you go through this loop again, and doing this over and over again will help the users continue to get the benefits of performance over a longer period of time. So now I want to close this talk by sharing some of my insights into doing this loop so far. So the first thing is to look at what are you focusing on as a key metric that you want to focus on for performance work. Right? Core Web Vitals are really good, but they are a very generalized version that is intended to work for all websites and all web pages. But you know your app the best and you know your users the best. So the first starting point is to understand what is the most important thing for your users. What is the golden workflow that is the most critical part for your application? So when talking about performance, VS Code maintainers mention that the most important thing that you really need to get to in a VS Code IDE is to launch the app and have a blinking cursor as soon as possible, so you can start working with your files. In terms of Postman, it could actually be launching the app and getting to a point where you can send a request as quickly as possible. Use this technique to find out what is most important for your app, instrument that, and focus your efforts into improving that workflow. Let me also cover a little bit into differences between lab and synthetic metrics versus real user metrics and field data. Some of the tools like Lighthouse and PageSpeed Insights help you get understanding of like where the problems are and dive a little deeper into what is causing some of these side effects. But they give you a single metric which kind of gamifies the whole system, right? But it doesn't give you a complete picture because you're looking at one sliver or one particular variant of the whole possible combinations in your app. The important thing to look at is what is your real user metric look like, right? What is the field data of the actual user experience for all of your applications? Tools like Lighthouse have now started to surface this information a lot more prominently these days, but they are again limited to only Core Web Vitals. Use this technique to find out what the business metric for your app is and collect that with the actual usages over time. Now it'll start to show like interesting insights to you, and you will immediately notice that performance no longer becomes a single number, but a distribution over different spaces. So in this case, you'll notice that like you have a really a high peak for average users, but you also have a long tail of users who are using your app under varying conditions, getting severely degraded experiences over time. The other caveat to know and understand is know and be aware of where your blind spots are. This is a graph that depicts the load times of Postman application across different platforms. And you can see a really fast experience for a large number of users who are using Apple Silicon hardware as compared to like Intel Mac or a normal Windows machine. So now if you are a developer and you are interacting with your app and you're interacting with your team who are primarily only using a really high powered hardware, you might be finding it hard to empathize with the users who are facing a degraded experience on low end hardware or low end network conditions in the extreme cases of the app usage. So understand where your users are from and try to simulate your lab environment to be as close to what your user environments are. Invest in tooling and hardware to help you get to that as much as possible. If you're not able to invest in hardware to get closer to that, use tooling like Chrome DevTools for network throttling and CPU throttling to help you simulate as much as possible to where your actual users are using your application. Finally, after all of these improvements, what you really want to make sure is not to ever face the same problems again. So simplest ways to do that is to set up like bundle size regression tests, which is very easy to set up and also very helpful in a lot of cases. But again, this only covers like one portion of the launch experience. You can also orchestrate end-to-end workflows for the key business workflow that you have identified using tools like Lighthouse CI or Webpage Test or Neuralink Synthetics. And I'm pretty sure there's a lot more like out there. This will help you cover tests for web applications. You can also use tools like Selenium or WebDriver to test parts of Electron that you cannot test with these technologies or tooling. So that's everything that I wanted to share that will help you kind of take some of the learnings of improving performance on web and extend them to Electron and also like vice versa. And if you feel this topic interests you, I've also linked to a few resources where you can dive a little deeper into it. And if you also want to reach out to me, feel free to reach out to me on Twitter if this topic interests you. So that's me. Thank you.